you don't know me, I'm Scott Lewis from the Associate Chair of the Department of Mathematics. And before I introduce our concluding speaker for today, let me put a plug in for tomorrow's symposium. We do have some schedules up here, and there's few of us, so take a bunch and spread them around to friends and neighbors and whoever. These are fantastic talks, and we would hate for them to miss out on it by not knowing about it. So without further ado, let me introduce Dr. Violeta Vasilevska. I have a hard time with that last name. But Dr. Vasilevska comes to us with a PhD from the University of Tennessee in Knoxville. She's worked at the University of South Dakota, and she's been here with us for about 4 years now, and a wonderful colleague. She has many areas of interest for her research, including topology, group theory, and math origami design, which I think we get to see something about today. Her educational interests really are to use origami and to introduce teaching, and undergraduate teaching is really involved in that in certain ways. And I think maybe we'll hear a little bit more about that. She's involved in many STEM committees, and she has been the director of several outreach programs. The one that we have has been available to us here is called Math Girls Rock. If you don't know about that, I think you could probably ask her afterwards. She'd be glad to tell you. But that is funded by the Mathematical Association of America and is basically used to promote and help promote the value of education to female students. Her hobbies include, more than mine, traveling, yoga, origami, of course, stamping, hiking, ballroom and folk dancing, amongst other things. So without further ado, I give to you, Dr. Vasilevska.
Thank you. Thanks all for coming, and I hope you will have fun I have fun when I talk about origami, so I'll try to be outside of the light because I don't like it. So I'll be talking about origami math, and I will tell you how much fun that can be if you want to do it. So I will start with a little bit of what is origami and the history about it, and then I'll talk about mathematical origami. And then at the end, I'm hoping to have time to talk about some practical application. And I'm hoping that you will be amazed like I was when I found out that origami are used in so many fields and in so many, and they have so many practical application in the real life. Origami is a Japanese word that is origami means paper folding. It comes from two Japanese words, ori, that means folded, and kami, which means paper, and I have no idea if I pronounce them well, but this is where the name from origami comes from. And it's basically just a think of paper folding, nothing else. You take the paper and you fold it, and that's origami, that's paper folding. There are several conjectures when and where the origin of origami is, and most of it is that it comes from Japan, China, and Europe. And if you search internet, most of the hits that you find is that it's come from Japan. But the point is, we're talking about paper here, and paper is dissolving, so you don't have very much proof that something existed and how long it existed. So we can just talk about it, but not knowing for sure. In Europe, there are few things that are still available for us to see. In the 15th century, from the 15th century, there is an origami boat, and what was interesting for me when I was searching about this, that baptismal certificates in the 16th and 17th centuries, they have been folded using origami as a cross, which was kind of interesting to see. Japanese classical origami that has been preserved is, the oldest document is a short poem that talks about origami butterflies in a dream. So as I said, we can just talk about it, but we don't really have to see it. And then it was interesting to see that origami was included in the manners of samurai warriors. They exchanged gifts that were strips of paper folded with origami, and they were exchanging gifts and call it noshi with each other. And then in Japan, they have been using origami as a ceremonial origami a lot. So before we start and have fun with origami, I would like to introduce, I would like, if it works, to watch a video about the artist Robert Lang. He is one of the most famous origami artists who is, who left his job just to start to do origami as a full job. And let's hear him what he has to say about origami and what we are interested about, Matt. Or maybe I should say what I'm interested in, origami and Matt. Yay, it's working.
One of the questions that our customers ask is, tell me something I don't already know.
What are we going to see in 5 years with the combination of data, cloud, social, and mobile?
This is not part of what we want to watch.
I probably started as an origami practitioner before anything, because I took up origami when I was 6. But in high school, I got interested in math and science, and so I went to college and studied electrical engineering and then applied physics. But origami was always a passion throughout that time. And in 2001, I decided to make origami my full-time activity. Quit my job and devoted myself almost entirely to paper folding and origami. Right now, I've got work in the New York Museum of Modern Art and the Peabody Essex Museum in Salem, Massachusetts, and a pretty large show, about 40 pieces, at the Indianapolis Museum of Art. Most of my work is representational, and for that I'm inspired by the natural world. I love wildlife, I love the outdoors, and when I see animals in the outdoors, I'm inspired to come back and to try to recreate that emotional impact with a sheet of paper. I use a lot of math in my work, and that's because what's possible in origami is defined by the mathematical properties of a folded sheet of paper. So if you understand the math, you can use it to create a lot of forms that you probably wouldn't have discovered just by trial and error. And math is much broader than what you might think. Just as most people's thoughts of origami might be cootie catchers and toys, most people's thoughts of math is arithmetic and quadratic equations, stuff like that in high school. Math is much broader than that. It's the study of shapes and relationships and forms and information. And the aspects of math that come into origami are often the math from this much broader world about relationships and shapes and forms.
So as Robert Lang, I've been interested in origami for a long, long time, but as him at the beginning, it was just having fun, doing some fun stuff, folding some animals or flowers and stuff like that. And then in 2005, I went on a conference and attended a workshop that was led by Dr. Tom Hull. And the workshop was on origami and math, and I was really intrigued by the name, because I said, okay, I know what is origami and I have done it, but math, what are you talking about? So I went to the workshop and I was fascinated. I was fascinated how math is behind everything that we're doing in origami, and how can you use it in teaching, in research, and you connect everything. And I was stunned. I have passion for origami. I love doing origami, and I love math, and I love teaching, and I can have all of it in a same plate. That's awesome. So that's from there on. I started using origami in my undergraduate teaching, and right now we are starting doing some research on origami design with colleagues from BYU and from here. And it's great because Robert Lang is visiting BYU because they have a grant for this. So we got to visit with him and talk to him and talk about research with him, which is great. Tom Ho said something that origami is a great way to get dirty with mathematics, and I fully agree with this statement. It's awesome. You do origami and you do math with it. I will talk about mathematical origami at the beginning, and this is the art of origami, as Robert Lang was telling about, is not just an art, it's much more than that. When we talk about mathematical origami, we as mathematicians, we are interested in mostly about these three aspects. We are interested origami as a puzzle. We are interested to design complex model just using one piece of square paper. And then we are interested about the crease pattern that he was talking about, and I pointed on the video when a machine was doing something like this. That's what he's creating. He's creating crease pattern that he's using later to do these complex models. So I'll be talking about these three aspects, and then we'll go and talk about practical application of origami. So first, origami is a puzzle. So when we think about origami, we mostly think about a piece of paper and you fold it and you get a bird or crane or whatever. With the modular origami, it's a paper folding when you use many pieces of paper. First you fold units, and then you take these units and you fold them together to get this modular origami. What's interesting about this, the individual piece of cake to fold it, but it's a very big challenge to assemble the final model using these units. And when I talk about units, there are different types of units, and I can find it one, and if not. So one of the units that I'll be talking about are these units. So this is the units that I'm talking about. So you make many of this, and then you use it, and you make this fun stuff, or you make the soccer ball. Well, these units, particular units that I'm holding in my hand, was invented by Tom Kuhn, the same person that I took the workshop with. And he called it Fizz units just because from these ones you can make pentagonal faces, you can make hexagonal faces, you can make also other faces, but they will not be called buckyballs. It's with these units, each vertex must be cubic because you can just connect 3 of them to make a vertex. So a polygon that has this kind of properties, they're called buckyballs, named after an architect, Buckminster Fuller, and they were very, this kind of polygons were of interest of the chemists in the 80s because apparently they describe molecular structure of various carbon molecules. So if we have chemists here, they can confirm that this is true. And I see you nodding. So I said that I'll talk about origami as a puzzle. So let's see what's the puzzle. In the 19th century, the Dutch mathematician William Hamilton invented a puzzle, and he called it Around the World. So what was the puzzle? So he said, take a dodecahedron. So dodecahedron is a polygon that has 12 pentagon faces. So we have pentagon, pentagon, 5 here and 5 here. So we have 12 of them, right? And he said, take the vertices of a pentagon, and on each vertex name it with a famous city that you want to visit. So we have London, Paris, Rome, etc. And he said, choose your favorite one that you want to start with, and then go around the dodecahedron, every city without visiting a city twice and come back to the city that you started with. Find a solution. Well, it's a puzzle, and it's a great puzzle, but it's not very interesting because there are many solutions. So you can do that and find solutions and paths and go around the world and come back to the same city in many different ways. How math is behind this? Well, in graph theory, we talk about this stuff that are called graphs, and this is actually graph of a dodecahedron. So how can we see that? Well, if I put my dodecahedron like this, and if I imagine that it's elastic, and I can stretch this face, stretch it and then push it down, you can see that this faces this one, up faces this one, and then we have 5 pentagons, so this is really two-dimensional representation of this three-dimensional object. And then, using this, we can start with this vertex, for example, go around, visit every other vertex once, and come back to the vertex that I started. And this is a solution to the Hamiltonian puzzle, right? And this path is called Hamilton circuit. So this is where math comes from. But as I said, this is not very interesting because there are lots of paths that you can construct. So this puzzle is not as it is, it's not very interesting. But let's add a flavor to it. What if I want to make, look at this dodecahedron, but I want at each vertex to have different colors? Well, using the path that we found it, we can use it to color the path, and then using a third color to do the rest of the edges, and now you have 3-colored graph. Why is this important? Remember what I said, that this was a two-dimensional representation of this three-dimensional object, which means the edges of this object correspond to the edges of this one, the vertices correspond to the vertices. So now our challenge is to go back to origami and see what we can do with this. Well, what we can do using this solution is to make this kind of buckyball that has at each vertex edges with 3 different colors, and that's a challenge. For this one, maybe not very much. Try to make the soccer ball with 3 different colors. If you don't have the math solution, very hard. For this one, try and error, maybe you can get to it. And I've been doing this with my outreach program with the high school girls, and they always love this. But we also have done not buckyballs, but tortoise. And this one is not 3-colored because I was too lazy to do it, but it's still beautiful. So this was one of the puzzles. Another puzzle that I wanted to talk about is this one. These are 5 tetrahedra. Okay, it should be tetrahedra that is damaged right now. So 5 of these pieces to intersect like this, and you get 5 intersecting tetrahedra. What's so interesting about this? Well, first of all, it's really hard to make it, but after you make it, it's really rewarding because you feel great. And it's a static model and uses this kind of units. So you make this kind of units, and then you make the tetrahedra, you intersect all of them, and you got this. So what's so stunning about this model? Well, if you take this model and put it in a dodecahedron, this model inside, each of the vertices will be vertex of the dodecahedron. So if we connect these ones, we get one face of the dodecahedron. It's a pentagon. It's beautiful. And what is so beautiful, and where is the math here? Well, when you try to connect all 5 tetrahedra here, you need to use symmetries. And this model here has all the rotational symmetry of this one. So starting this, you study this, you study this, you study this. It's awesome. So as I said, you use math, this rotational symmetry of the dodecahedra to put all of these pieces together, and that's the most challenging part. Making the tetrahedra is a piece of cake. after you get used to it. Okay, so another thing about origami is that, and as I said, I've used some of this in my my classes, and one origami project that I usually use in my geometry classes is the next one that I want to talk about. So, oops, I went too far away, right? Oh, okay. Forget about the problem that I wanted to talk because the slide is not here. Let's talk about, if this wasn't challenge for you before, if this is not challenging and this is not challenging, you can search the internet and you can find all of this modular origami and you can try to fold it. I haven't folded any of it, but it's on my to-do list. Okay, so the project that I'm using usually in my geometry class, that I usually want to give to my students is, in geometry, there are construction problems that are not solvable. So if I give you a collapsible compass means you can draw the circle, but then if you want to draw the circle over there, when you go, it will collapse. So you cannot preserve the distance of the radius, right? And if I give you a straight edge with no markings, you cannot possibly do trisecting of an arbitrary angle, or let's talk about trisecting an arbitrary angle. So if I give you the angle and straight edge and collapsible compass, in general, you're not able to trisect the angle. But what's so amazing about origami, if I give you just a piece of paper and I tell you just form an angle and trisect it, you will be able to do it, just fold it, which is amazing. And after that, you can even prove using math that the angle that you found is really 1/3 of the angle that you started with. It's a great project and I love it. And it's amazing. I mean, something that cannot be done with something that you're used to do, it can be done just by folding. And the next thing about mathematical origami that we are interested in, as I said, we work with some colleagues from here and from BYU, is origami design. Remember at the beginning I said we are interested in 3 aspects of origami. Origami is a puzzle, and I talked about puzzles. And then the next 2 were take a piece of paper and fold it to get this amazing complex models here. This is Basel, this is Orban. Try to do it. That's a challenge. And also the third one was the crease pattern. The crease pattern is a diagram that contains all folds of your model. How to do that crease pattern so you can use it and make all of this. That's another challenge. So that's what I'll be talking with this origami design. Robert Lang had he has a lot of publications, but the one that we have been looking at is Origami Design Secrets, and he has a lot of folding and a lot of math proving it, and it's a great book. And what he is doing is the following. He takes the model. So let's say we want to make a bull moose. Well, we know how the bull moose looks like. So first thing that he is doing, he is making this stick figure. What is this stick figure? It is called 3, by the way. And each part of this stick figure is a body part of the moose. So we have the body, we have the legs, we have the head, etc. And then he uses this stick figure, the tree, and he's trying to make the crease pattern. So this is the crease pattern. This is the challenging part. This is the challenging part. But that's okay. You need to use a lot of math. You need to solve a lot of stuff. But using math and using the computers, remember I pointed out that stuff. You can use math and use computers to create this crease pattern. That's a hard but manageable. And then with the computer you can do this in 5 minutes. But coming from here to the base, it can take a few hours or more. That's the most challenging part. After you do that, then the final model will be just using the base and just putting all of these little touches. If you want slimmer legs or bigger legs, if you want a bigger hat, a smaller hat, and stuff like that. But this is the most challenging pattern. The crease pattern used here uses a polygonal packing. So all of these are polygons. Well, the point is, some crease patterns can give you a good folding pattern, but not all of them will give you the easiest one. So for example, for this particular moose, if you use different pattern that I'll talk in the next slide, will not give you an easy folding pattern like this one. So this is used for this. So this is another challenge, to try to find a crease pattern that will give you not just the model that you want, that will give you the easiest way to do it, because the folding steps are also important. So if you look at the scorpion, for example, we want to make the scorpion, then again, we can make it a tree, and then we can use mathematics and a computer to make this crease pattern. And if you can see, on this crease pattern, we have circles. So now we have circle packing. Circle packing is a huge area in mathematics. Robert Lang, in his talk, usually he wants to say that this is great because now you can use the work of dead people to do what you want, because you're using results from people that they have done this. So you do the circle packing, and if you notice, every circle here is a part of a body. This is this part, right? And then we have 4 legs on each side, so 1, 2, 3, 4, 1, 2, 3, 4. And then we have this, that I don't know how they're called in English. And then we have these small things over here, 2 more circles, etc. Each circle is part of the body that you fold, and and then if you want this part to be slimmer than this one, you'll do more folding there. But that's after you make your base fold. Now, so this is what we are interested in right now. You're looking at this origami design, and actually, more particularly, we are interested in his next book that he's just writing about crease patterns of tessellations. Tessellation is a collection of figures that is filling a plane with no gaps and no overlaps. So use for example, you use a hexagon, and you can fill the plane with hexagons, and there will be no gaps and no overlaps, and all plane will be covered with hexagons. So you can use and find crease patterns for these kind of tessellations, and you can do all of these beautiful models. And one book that I really like and has a wonderful patterns is Origami Tessellation from Eric Jardy. As you can see, my pronunciation with names is not really good, but he has beginners and advanced and more advanced folding crease patterns for tessellations, and they're beautiful. They're beautiful. Now, what was interesting that I found it about this tessellation, remember I said I'll talk about mathematical origami, and so far we have discussed all 3 aspects as a puzzle, the crease pattern that we need to take care of, and take one piece of paper and make a complex model. But I also said that at the end we will be talking a little bit about application of origami. So I was surprised when I searched that these origami tessellations, researchers are interested in them. And why? Because they compared the origami tessellation to the formation of cosmic structures from dark matter. I didn't know about it, but it was really amazing for me that you can take this kind of origami tessellation, you can compare with the cosmic structure, and you can look at the folds of these tessellations and maybe see how everything around us is folded. All around is folded. Next, we'll talk about practical applications. With this practical application, there are two problems that we are concerned about. One problem is, how can I have a piece of paper and fold it flat? A challenge. So how can a crease pattern be folded like that? And if it can, how can I do it? So that's one challenge. That's a problem of flat foldability. So for example, if you look at this pattern, how can I tell that if I fold this pattern, and one of the creases are mountains, one is valley. So this is the valley, this is the mountain fold. That's what they are. How can I look at this pattern and I can tell you that if it's a flat foldable or not? So if I fold it, how can I know that it's flat foldable or it will be crumbled and three-dimensional? Well, this is where the math comes in place again, right? There are four mathematical, oops, not yet. Sorry about this. Okay, so four mathematical rules for producing flat foldable origami crease patterns. First thing is, it needs to be colorable. So if you have the crease pattern, and if you color it such that no two touching regions are colored with the same color, you should be able to color it. If it's a flat foldable, needs to be two colors. So you can use just two colors and color it like that. So we can see that no two regions are colored with the same color. They're touching at the vertex, which is allowed, but they cannot be touched with an edge and with the same color. So that's the first rule. What is the second rule? Well, the second rule says that if you count at each vertex, the number of mountains fold and the number of valley folds, their difference must be 2, no matter in which direction. So it will be either plus or minus 2, right? So at each vertex, the number of the difference between the number of mountains and valley fold must be even number in order for that crease pattern to produce a foldable model. So that's the second one. The third one says at any vertex, interior vertex, if you number the angles, and if you add the odd ones, and then you add the even ones, both of these sums needs to end up to 180. That's the third rule for us to be able to get a flat foldable pattern like this one. And the last one is we cannot have a self-intersection of the paper. So if we folded the paper like this and I need to fold this one, I cannot go and intersect the paper like this. There's no self-intersection if we want to have a flat foldable pattern. So why we are interested, we will see why we are interested in this stuff, because if you have something that is flat foldable, you can put in your space shuttles and you can go into space and carry it, right? If it's huge, you can. So that's why we're interested in this flat foldable patterns. But what's interesting, and it can be given as a project in teaching, can you guess what is this pattern? Which model? A model that most of us has done it. It's the easy one. I'm sorry?
The crane.
Crane. It's a crane. So what's interesting, I have a crane that I will show you, but it's not this one because mine is a little bit more complicated, but it's valid in any case. What's interesting is if you fold the crane, unfold it, and then color your crease pattern and fold it again. Do you know what happens? Amazing stuff. You can get the crane that is colored with one color on one side, another color on the other side. The same thing. It's amazing. And you can prove that this happens it's a beautiful thing. Now, so one with the practical application of origami, so one problem is that we want to have a flat foldable model. We want to have a crease pattern that will give us a flat foldable model. The other thing is the rigid origami. What rigid origami means? So we have the fold, we have the crease pattern, and then we fold the model. Now, if we replace the paper, all of these parts with metal, and if we replace the creases line, the crease ones here, with hinges, can we still fold the model like we do with paper? Can we still do this? If we can do that, that's great. Why? Because, as I said before, the flat model I can put in a space shuttle and then go into space and then unfold it, deploy it, and I'll have a huge something that I want in the space, right? Now, some things are rigid foldable, some things are not. So, for example, this model here, it is flat foldable, and also it's rigid because I can take on these two ends, open, close, and I'm fine, right? Now, let's look at this model here. This model is not from paper. Oh, I need that. But I can easily unfold it. And it's great. It just is. Well, it's unfolded, but it's flat, right? But if I try to put it back together, it's a challenge. See how I did it with the previous two paper ones, right? It was so much easy and doable, and now because I'm presenting, I cannot do. Oh, okay, good. So now we can see that we can unfold easily, but we cannot fold it back easily, right? Like we did before. So this is not a rigid origami that we want. Well, this is another problem that we want to address with this practical application, because we do need this rigid origami. So what is done is the paper that I was folding and unfolding. Maybe you have noticed before. I mean, it can be done even smaller, not big like I did. So it can be even compact than this one. And probably you have seen it because a lot of subway maps or other maps are folded using this fold, origami fold, without even knowing, but that's the fold that they usually use. And this is called the Miura map fold. It's invented by the Japanese person Kuro Miura, and what is interesting about this fold, because this fold was used for solar panels. They constructed solar panels because it's a rigid origami, it's flat foldable. So they replaced this part with solar panels, and then they put it in a Japanese space flight unit in 1995. They went to the space and deployed it because it's very easily done. So what's good about this? It was, by the way, it was first origami in space. This fold was first origami in space in '95. What is good about this is because it's really foldable and unfoldable. It uses not very much of motor energy, which means you can reduce the weight and complexity of your space shuttle to bring this solar panel into the space, which is important, right? So this is one of the application of origami for doing these solar panels. Next, Robert Lang has worked with a German company on designing of airbags. This research is still ongoing, but he succeeded to came up with origami fold, origami crease for these airbags. And the good thing, an application of this was that the company that requested design of this kind of airbags in cars, they were able to effectively test these airbags without actually doing a crash, right? Which is great. I have video to show you how actually it works. So these are computer simulation, and maybe it's not working. Oh well. There is a simulation that shows how, because that's what the company is doing. They're using this simulation of origami algorithm simulation to do tests about this. So the video shows how from the crease pattern, it's a flat foldable, and then you expand, and from flat foldable you get the whole ear. I'm sorry, it always happens something, so I hope this is the last thing that happens. And as I said, this research, and this should be written here, that is hidden, that this research is still ongoing. They haven't found the final crease pattern for this. Next, who would say that origami can be used in medicine? Isn't that amazing? In 2003, two researchers from University of Oxford, they developed an origami stand. And of course the picture doesn't look nice, but so they developed this origami stand. The stand can be used to enlarge. So if there is a patient with a clogged arterial vein, you can use this stand so they can enlarge the vein and the blood can go through it. So what they have been doing, the good thing is that the stand is a tube that can be collapsed in a very small size, and then they use a balloon catheter. Is it catheter? So they use this and to maneuver the stent into the arterial vein until the place where it's clogged, and then they inflate the balloon which enlarges the stent, and then when the enlarged stent is there, the place that it should be, enlarge the vein, and then the blood flows through it, and it can stay permanently there. No problem about it. The organ tissue will go around it and everything will be fine for the patient. Isn't it amazing? Just using origami folding, you can do all of this stuff and use it even in medicine. The next thing is Ruben Lang had requests from the Lawrence Livermore National Laboratory to construct a crease pattern for a space telescope. They called it eyeglass. And what Robert Lang did, he used this crease pattern, which is flat disc or annulus, and then you can do all of these steps until you get this flat piece of paper like a cylinder. So why this is important? Because if you take the telescope lens and you fold it nicely as a telescope in a small size, you can put in your satellite and go into space. And because we do need the telescope lenses in the telescope because we want to see what's happening in the galaxies around us, right? So far they have. In 2002, I think, they managed to fold telescopical lens from 5 meters to 1.5 meters. But they're hoping that soon they can manage to fold 100 meters of telescopical lens into 3 meters so they can go into the space and deploy it. That's the goal of this, but I'm guessing they're on the right track. And then I just searched origami practical applications, and I got a bunch of hits. And one that I saw it was this article about DNA origami technology for biomaterial applications. And I just put the abstract of it. And you can see what they're saying at the end. The DNA origami technology has practical potential in various research fields. It's not just this. So the practical applications are huge. And another thing that I found, that this is the most recent, in April 2013, few Japanese researchers, they created a nanopaper antenna. We need antenna for everywhere, right? For everywhere. They created this nanopaper antenna, which is sensitive for a wide range of frequencies, and can be folded into a paper crane. So you have this paper crane, and you can use it as an antenna. Well, of course, they use a particular type of nanofibers, and then they use something else. So they use other technology, but the point is they use origami to do this antenna. So what is good about using this kind of antennas, paper antennas? Well, first of all, they're foldable. They're of small size, which means the devices that you are putting in can be smaller, not huge, less stiff. Another thing is that depending on how you kind of fold the antenna, it can perform differently. What I mean, so that's for the future research. You take antenna, you put your device. If you fold it one way, it can measure your temperature. Fold it the other way, it can measure your blood pressure. It's a lot of options. I mean, you saw the Chris patterns. Different Chris patterns can give you the model, but not exactly one. It can differ. So there are a lot of potential about applications of origami in the real life. If you're interested, just as I said, Google origami practical application. You get a lot of hits on it. At the end, just a few fun facts. If you want to look about origami, the three top person, not exactly in this order, are Tom Hull, Eric DeMay, and Robert Lang. So I talked about Tom Hull was the professor that I took the workshop of, and I was excited about that I can connect my origami, my math, my teaching, and research, everything. And then we talked about Robert Lang. He is the famous origami artist. And Eric DeMay, he is the youngest professor at MIT. He's computer science. He is awesome, and he has. I have been to several of his talks, and he is just amazing. He is using mostly computers to do all of this stuff with origami and paper folding. If you visit his website, I mean, you can see what he has been done and what he's been doing and what kind of stuff he's been interested in. In addition, his father is an artist. So together with his father, they're doing amazing stuff. And you can go on his website and you'll see what kind of art they have been doing. At the end, I have just a few of the resources that I used. This one is the one that has various practical origami applications. What has been done recently or done before, a lot of papers that you can read and stuff like that. Thank you. And I forgot just this, I'm sorry. There is a movie, it's a documentary movie, it's called Between the Folds, and it's about origami. It's a short movie, but it's really beautiful.